Hey guys, so we are back to virtual screening one again. So as we mentioned during the course, virtual screening is an umbrella term for any method, computational method, in silico method we use to prioritize compounds before testing them experimentally, right? So now we're just going to try and show how to implement a few virtual screening protocols, like maybe you are looking for compounds to a set of log p values, compound to a set of solubility values, compounds that obey the rule of 5, maybe Lipinski rules, or the rule of 3, maybe compounds in the fragment size libraries, and so on and so forth. So this is the basic virtual screening, or compounds that have a particular scaffold or whatever. So this is the basic, and then we're also going to look at, in a particular chemical space, how do you abstract a section of some molecules and so on and so forth. So this is what we're going to look at. So this is fundamental virtual screening. And if you're actually working on chemical libraries, this is the place to start, because libraries are designed to have a whole lot of properties across the space, I mean the chemical space. So now we're going to start by installing some libraries. Most of them are already installed for me, so I might just as well comment this out, but maybe for you, you might want to install them. So I'll just load the libraries. Okay, sorry, let me activate my environment, I mean my interpreter. So I'll load the libraries. Then I've prepared a data set. So the data set is from it's from a chemical database of compounds. So I think there are just like 2,000 structures available, which I've provided in CSV formats with their smile notations, and I think probably just their names or something like that. Yeah. So I got them from Enamine database. So Enamine is a proprietary chemical vendor. So it uses combinatorial chemistry, whatever, to provide its compounds that are synthesizable on demand. So let's load our data set. So we read it using pandas, and then you can see I have 2,000 compounds. So you can see their names, En for enamine, and then their SMILE notation. So this is our data set. So and like our template or example data set containing 2,000 compounds. Now, first of all, to be able to characterize, as I mentioned, to be able to characterize compounds, I mean, chemical structures, you must describe them. And we started by showing, basic molecular descriptors, molecular weight, log P, number of hydrogen donors, acceptors, on and on and on. And even to an extent, you can even go to advanced way of describing the molecule. You go into fingerprints, circular fingerprints, and all that of them. You can even go into graph-based fingerprints, where the atoms are represented as nodes and the bonds as edges, and so on and so forth, as we have seen in the model. So, but today we're just going to show some basic descriptors, because most times working with databases might not require serious sophistication. It might just be some basic properties that we want to use to classify or segment or even describe the database. So we're just going to compute the molecular weights, log P, TPSA, donors, acceptors, and rotatable bonds. So from the smile column of our DF data, then we have a descriptor function. Yeah, so we create a function for molecular weight. This is actually a set. Yeah, so a set mapping molecular weights with the calculations involved in retrieving it, and then we define a function to compute it. So now let's see what it looks like. So it's just going to take some seconds. So we can see now that we have our compound, because we've merged the DF with the descriptors, and then we have the full data frame now. So our compounds, our SMILE notations, the molecular weight has been appended, log P, TPSA, donors, acceptors, everything has been provided. right? So now we have a basic characterization of our database. So if we want to classify this database, want to segment it, want to filter, we have some set of properties from which we can do the filtration, right? So we can look at molecular weights, maybe less than 200 or whatever. So that's actually what we're going to do. So first, we're just going to implement the rule of five filtering, the Lipinski rule of five. So what is Lipinski rule of five? Molecular weight should be less than 500. Log P should be less than 5, donor should be less than 5, acceptor should be less than 10, and so on and so forth. So that's actually how, so we're going to apply it on this, our data set now, df with descriptor. So we apply this algebraic expression on it, and then how many compounds will remain? Let's see. Okay, obviously it's just one compound that is out of the, so all our compounds obey the Lipinski rule of five. Well, that is understandable because I got this compound I told you from a chemical database that has been well curated to serve the drug discovery community. So it is not out of place that all of them obey the rule of five. Do you get? So that's not a very big issue. So now we can also look at the rule of three. In the module, I mentioned fragments. So fragments obey the rule of three. Molecular weight less than 300, and every just three multiples of three. That is why it's rule of three, because it's necessary in fragments drug discovery. We need to have smaller compounds with, let's say, an appreciable binding affinity, and then we can reconstruct, we can build on it until we achieve it's like de novo design of drugs. So you might want to get a database and say, oh, I need fragments, get me fragments, I want to work with fragments and all that. So the same way, so let's display compounds that obey the rule of three. So there are only 8 compounds that are fragments in our whole data sets, that their molecular weight is less than 300. You can see just 8 compounds. So if you want to do this filtration, you might just run this code and that. So now that is the first thing. Another thing that is important is similarity. If we can describe our compounds, we can also determine which of them are neighbors and which of them are distant from each other. So, and that is important in grouping your compounds too. So if you say, oh, if all the log P are around two, let's say log P of 2, everyone that has log P between 1.8 and 2.2 are neighbors, or maybe molecular weight, so and all that, just like it's similar to this rule of three filtering. We now believe that all these compounds here, these 8 compounds here, are neighbors. All of them are fragments. So it's same way for similarity search. Yeah, but similarity search usually takes another shape because it can depend on a whole lot of more descriptors or more features than just these simple features we described here. So usually, to do a similarity search, as we mentioned in the module, you must compute a descriptor. For example, here we're generating fingerprint, the Morgan fingerprint. So with the Morgan fingerprint, each molecule now have an identity, and you can decide to start comparing the identity. So this thing I call encoded in bit size of 2048. Yeah, and then radius of 2, because it's a circular fingerprint, as we mentioned in the lecture. So we're going to compute RDKit Morgan fingerprint for all our compounds. Yes, for all our compounds, and then we are going to determine which of them are most similar, which of them are most distant. So let's see. It just takes some few seconds to do the computation. Our compound set is very small. Okay, so it's been able to tell us which of our compounds are most similar. So similarity, that is this first index, and then the ID number of the compound. Compound 9 and 37 are essentially the same compound because their Tanimoto similarity is 1. Remember, we introduced Tanimoto similarity, right? The ratio of intersection over union minus intersection. So, and then for the most distant molecule, their similarity is actually 0.02, and it makes sense. And it's between compound 27 and compound 1, 1863. So now we can actually decide to display this compound. Let's see. Oh, let's see. Okay, these compounds are similar. What are they? Obviously, as I mentioned, these ones have tiny motor of 1. It means they are exactly the same compound. Yeah. So maybe in our database, we actually have a duplicate. Okay. Yeah, yeah. We have a duplicate. So now we've been able to convert it to a more grid image. So let's see whether we'll be able to display it. So you can see here that our molecule, we set the most image similar, that is the similar molecule, they're essentially the same compound. So it was a duplicate. That's why it was able to return it. So that's not actually what I intended, but maybe I said my data set has a duplicate. I should have filtered duplicates, right? So essentially here at this step, right, I should have computed the canonical smice again and removed duplicates. Because if I've done that, I would not have ended up with exactly two compounds that are going to be this similar. So let's look at our compounds that are very distant relatives. Oh, my compound is not showing up. That's too bad for me. All right. So the next is clustering. I've been mentioning filtering your compound, grouping your compound, which of them are neighbors. So when you identify which of your compounds in a particular database or data set are neighbors, how do you group them? So there's a lot of ways to group your compounds. The easiest way is a distance-based method like k-means clustering. Right. So chemist clustering allow you to define the number of clusters you want. Let's say, oh, I want 10 clusters for this, my compounds, right? And then, oh, so it will define 10 different, initialize 10 different nodes in your chemical space. And then it will start assigning each molecule to each node depending on the distance of each molecule from. So I think it uses Euclidean distances. So obviously it will compute fingerprints as we mentioned before. It's going to use the anytime you are doing similarity clustering, you must have a set of features. I've been saying this. You must compute fingerprints and then all that. So we can look at that and then we do clustering, k-means clustering, and then as you can see here, it has added a cluster number. So for each of the compounds, I've assigned it a particular cluster between cluster 0 and cluster 9. So for example, compound 17 and 7 fall under the same cluster, 9 and 9, right? So as you can see here, their molecular weights are close. Their mole log P 3.592.7, TPSA 50 and 60. So there's a lot more criteria for classing them inside the main inside a single cluster, but I'm just showing you some basic things that might not actually be true. Okay, so let's visualize the chemical space with the different clusters. So you can see here now for now, as I mentioned, in chemical space is a way to visualize how spread out are our compounds along some coordinates represented by some features or some descriptors. So for example, we choose log P and molecular weights as the X and Y axis, do you understand, as the projection of our chemical space. And then we can see each of our compound in this chemical space. So for each particular compound, you can see, oh, it belongs to, or this compound is at this point, log P of 2 point something, and molecular weight of just above 200, and on and on. So these are the things you can see for the compounds. Uh, now as you can see, most of the clusters are modeled up, they are modeled up together, and that's not very nice. So to actually have a very clear separation of the clusters, you will need to do a PCA or a TSNE plot. So usually principal component analysis, so that it will show you the most important motions. I mean, the most important variation in your data set. So this, if you want more of this, I think tutorials has been clearly presented by Pat Waters. So and these Jupyter notebooks are available, so you can have a click on the link and then see some of the things Pat Waters have done. So this is just a basic representation of virtual screening. So it's not a complicated thing. It's just a way to select the molecules you need depending on variety of criteria. So, and don't forget, first thing is how do I featurize my molecule? How do I assign properties, descriptors to them? Then once you have done that, then the bulk of the work is done. You now start filtering based on your criteria, yeah, your cutoff and so many things. So some of them are automatic, as you can see here. Like for example, this K means clustering. We just define the number of cluster, but the assignment is automatic. Some other ones we are very clear about what did it do during the assignment. For example, when we did rule of 5 filtering or rule of 3 filtering, we are very clear, oh, these are the criteria. But some other times in clustering, you are not very sure. So these are some of the things that I can do. All right. Thank you for coming far. You are welcome.